In this topic, we're going to introduce the concept of work done by an electric field on a charged particle. We're going to define the term potential difference and talk about charged particles moving in electric fields. In this first video, we're going to talk about the electric potential difference. So solve problems using formula for work, convert from joules to electron volts, a derivation for the electric field strength based on voltage. Okay, so first I'm going to review some projectile motion material, and then I'll compare this to the topic that we've got. So let's consider a mass in the gravitational field of Earth. If it is free to move, it will accelerate down. So let's take this girl with a ball, for example. If the ball is released, it is free to move and it will go down. That is because gravity is acting on it and causing it to fall towards the Earth. As it falls, it gains kinetic energy. However, we also know energy cannot be created or destroyed. It can only be transformed. So this energy has to come from somewhere. So we can say that the ball in this position up here has a potential energy, and in this case it's gravitational potential energy. Okay, so now I'll compare the same scenario but with electric charges. So if we consider a charge Q and its associated electric field. Now it's a positive charge, so you can see the field lines radiating outwards. If a test charge is placed at B and it is free to move, it will actually accelerate away from Q. Q is a positive charge, B is a positive test charge, so they will repel. So B will actually accelerate away from Q. So by doing so, it gains kinetic energy, and to account for this, it must have had energy to begin with, and that would be the electric potential energy. So I've got 4 examples here that can help us describe the energy transfer in electric field. So let's start with this positive charge near a negative charge plate. You can see the field lines going down. So what that means is when we've got a positive charge in the area, it will follow the field lines. If the positive test charge is free to move, it will move in the direction of the field lines, gaining kinetic energy, losing its original potential energy. However, if we have the same situation, we have a negative test charge, and we want to pull it down, this charge will naturally want to repel away from this plate. However, if we pull it towards a plate, we're increasing its potential energy. Our example 3 here, we've got the positive test charge being brought towards the positive plate, again gaining potential energy. Now, 4th example, if this charge is free to move, it would naturally want to be attracted to this plate and it will gain kinetic energy, lose potential energy. Both example 1 and 5 relate to our previous example where we had the ball in the gravitational field. If we release the ball, the potential energy transfers into kinetic energy. Now we can define the electric potential difference between 2 points in an electric field is the work done per unit charge in moving a positive test charge between the 2 points. So we can see the potential difference is the work done per charge, and we can provide an equation here. The units are joules per coulomb, or the more standard unit used is volts. So if a charge moves in a direction opposite to the force of the field, work is done on the charge. So the field in this example is going up, the charge is going down, so it's opposite direction, meaning work is done. By the law of conservation of energy, the work done increases the potential energy, and this is given by this equation. So the change in potential energy is actually the work done. Again, if the charge moves in the opposite direction, the change in potential energy is equal to the work done. However, this also translates to the kinetic energy. When we're talking about electric fields, we often use numbers that are very small. And when we use the standard unit of joules when talking about work, the numbers can get difficult to manage. So we introduce the unit of electron volts to help us manage this. 1 electron volt is the work done when an electron moves through a potential difference of 1 volt. So, for example, if an electron moves through a potential difference of 300 volts, the change in potential energy is 300 electron volts. If a nitrogen ion has a charge of 3 electron volts. If that moves through a potential difference of 50 volts, then the change in potential energy is 150 electron volts. So if the work done is equal to the change in potential energy, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Now I'm going to run through a derivation of the electric field strength in a uniform electric field. So let's consider a uniform field first. And x and y are points separated by some distance that are parallel to the field. So the potential difference between x and y is delta V. We already know that as the field is uniform, electric field strength is constant in magnitude and direction. So therefore, the force on the charge is the same throughout the field and is given by this equation. Now if we move a charge from x to y, the work done is given by this equation. So what we can do, we can use these two equations and equate them. So we know work is equal to force times distance, and we know the force is equal to EQ, so we can substitute EQ for the force, and we get this. And we also know that work is equal to Q delta V, and this is where we equate the two. So then rearranging the equation to find the electric field strength as our subject, we get electric field strength is delta V over D. So this formula gives us an easy way to calculate the electric field strength between two parallel plates, for example, where we have our uniform field. So we can calculate electric field strength that way. However, we also still have our other equation to calculate electric field strength.